A highly advanced vision system scans the road ahead, processing millions of pixels every second to guide a 3-ton machine moving at highway speeds. The camera registers an octagonal red sign at the upcoming intersection, but instead of applying the brakes, the system accelerates. To the human driver, the stop sign was perfectly clear, marred only by a few small, seemingly random stickers placed on its surface. To the machine, those carefully calculated stickers completely altered reality, transforming a universal command to halt into a speed limit sign. This catastrophic failure was not a glitch, a hardware malfunction, or a simple software bug. It was a targeted manipulation of the system's underlying logic. This scenario perfectly illustrates the chilling reality of adversarial attacks. These are deliberate, mathematically precise interventions designed to break the fundamental perception of artificial intelligence. By introducing subtle alterations to input data, bad actors can force a highly sophisticated system into making a glaring error with absolute certainty. The phenomenon exposes a massive blind spot in modern technology, proving that how a machine sees the world is fundamentally alien to human perception. We are building our future infrastructure on systems that can be easily manipulated by invisible mathematical noise. The ease with which these systems can be compromised raises profound questions about what it will mean for our reliance on automation. If a few pieces of tape can trick a car, or a layer of static can deceive a medical scanner, the fundamental trustworthiness of our digital infrastructure is called into question. We are rapidly deploying these technologies into high-stakes environments, assuming that their superhuman accuracy and controlled tests will translate to flawless performance in the chaotic real world. Yet the existence of these exploits proves that high accuracy does not equate to true comprehension. To understand why AI can be fooled so spectacularly, we must examine the architecture of the neural networks powering these systems. The current era of artificial intelligence is dominated by deep learning, a method where algorithms process data through multiple layers of interconnected nodes. These networks do not learn concepts. They learn highly complex statistical correlations across vast, multidimensional spaces. When a model looks at an image of a cat, it does not see fur, ears, or whiskers. It sees a specific distribution of pixel values that, during its training phase, was statistically associated with the label of a cat. This reliance on statistical patterns creates inherent deep learning vulnerabilities. Because the model maps inputs to outputs using complex mathematical boundaries, there are inevitable gaps and jagged edges in those boundaries. Researchers demonstrated this early on with a now famous experiment involving an image of a panda. The image was fed into a state-of-the-art vision model which correctly identified the animal with near-perfect confidence. Then the researchers applied a carefully calculated layer of digital static to the image. To the human eye, the altered image looked exactly like the original panda. But to the neural network, those imperceptible modifications shifted the data points just across a mathematical boundary in its high-dimensional space. The model now classified the image as a gibbon, and it did so with 99.3% confidence. The noise was not random. It was generated by running the network's learning algorithm in reverse. Instead of adjusting the model's internal weights to better recognize the image, the researchers adjusted the image's pixels to maximize the model's error. The implications of this mathematical fragility are staggering when applied to physical infrastructure. Autonomous vehicles rely entirely on continuous, accurate classification of their surroundings to navigate safely. A misclassification in a laboratory setting results in a funny research paper about a panda, but an AI misclassification on a busy highway can result in a fatal collision. The physical world is inherently messy and unpredictable, providing countless opportunities for both intentional sabotage and accidental adversarial conditions to manifest. Researchers have repeatedly proven that these attacks do not require direct access to the vehicle's internal computer. They can be executed entirely in the physical world. By placing precisely designed patterns on clothing, individuals have rendered themselves completely invisible to pedestrian detection systems. By slightly altering the texture of a physical object, researchers have tricked robotic arms into grasping empty air. The visual world we take for granted is, to a neural network, a fragile construct that can be shattered by the right sequence of shapes and colors. This reality has triggered a quiet crisis within the autonomous driving industry. Companies that once boasted about the flawless accuracy of their vision systems are now spending billions to address these blind spots. The focus has shifted from merely recognizing objects in ideal conditions to maintaining stability when the input data is intentionally hostile. Engineering teams are forced to rethink their entire sensor fusion strategies, realizing that relying on a single modality like a camera creates an unacceptable single point of failure. The threat extends far beyond the roadways, penetrating deeply into the healthcare sector. Modern medical diagnostics increasingly rely on machine learning models to analyze imaging and tissue samples. These systems often outperform human doctors in detecting early signs of diseases like cancer or diabetic retinopathy. However, researchers have demonstrated that adding a tiny, invisible layer of adversarial noise to a benign medical scan can cause the model to confidently diagnose a malignant tumor. Conversely, a scan showing a massive tumor can be mathematically smoothed out, prompting the system to declare the patient perfectly healthy. The stakes in medical imaging amplify the urgency of the problem. A compromised diagnostic system could lead to widespread medical malpractice, incorrect treatments, and devastating patient outcomes. Furthermore, the financial incentives in healthcare billing could motivate bad actors to deploy adversarial techniques to manipulate diagnostic software, artificially inflating insurance claims by forcing models to detect diseases that do not exist. The intersection of vulnerable algorithms and high-stakes financial or medical outcomes creates a dangerous landscape that regulators are currently ill-equipped to police. While image manipulation often dominates the conversation, the auditory domain is equally susceptible. Voice-activated assistants and biometric security systems process sound waves through similar neural network architectures. By embedding hidden commands within a recording of a song, or even within ambient room noise, researchers can issue silent directives to smart speakers. A human listener hears nothing but a faint crackle or a generic pop song, while the machine hears a crystal-clear command to unlock the front door, transfer funds, or disable a security alarm. This auditory vulnerability transforms everyday devices into potential Trojan horses. As our homes and offices become saturated with always listening microphones, the attack surface expands exponentially. The assumption that audio commands must be audible to humans to be effective is fundamentally flawed. We are sharing our living spaces with entities that perceive a hidden layer of reality, a frequency band of mathematical signals that we cannot detect but which absolutely dictate the behavior of our digital environment. The frontier of adversarial research has now expanded into the realm of natural language processing and large language models, or LLMs. These text-based systems do not process pixels or audio waves, but they still map inputs to outputs using statistical weights. By appending specific, seemingly nonsensical strings of characters to a prompt, users can bypass the safety guardrails programmed into the most advanced chatbots. These adversarial suffixes act as a skeleton key, confusing the model's ethical filters and forcing it to generate restricted content, from malicious code to instructions for synthesizing dangerous chemicals. These text-based jailbreaks highlight the immense difficulty of securing systems that are essentially black boxes. The creators of these language models attempt to patch these vulnerabilities as they are discovered, adding the specific adversarial prompts to their training data to teach the model to ignore them. However, this reactionary approach is fundamentally flawed. It is a perpetual game of whack-a-mole, where patching one specific exploit does nothing to close the infinite number of other mathematical loopholes that exist within the model's billions of parameters. To combat this pervasive fragility, the artificial intelligence community is racing to develop robust AI defenses. The most common strategy is adversarial training. This involves intentionally generating thousands of adversarial examples and including them in the model's training dataset. By explicitly teaching the neural network what a manipulated image or audio clip looks like, developers hope to smooth out the jagged edges of the model's decision boundaries. The goal is to force the system to rely on more fundamental, robust features rather than fragile statistical quirks. While adversarial training improves resilience, it comes with severe trade-offs. Training a model on hostile data requires exponentially more computing power and time. Furthermore, researchers have observed a frustrating phenomenon known as the accuracy-robustness trade-off. As a model becomes more resistant to intentional manipulation, its overall accuracy on normal, clean data often drops. The system becomes so paranoid about being tricked that it begins to second-guess its own legitimate perceptions, leading to a degradation in baseline performance. Other defensive techniques, such as gradient masking, attempt to hide the internal architecture of the model from attackers. If the bad actor cannot access the model's mathematical gradients, they cannot calculate the precise noise needed to fool it. However, this defense has proven largely illusory. Attackers simply train their own substitute model, generate adversarial examples against the substitute, and transfer those attacks to the target system. The underlying statistical vulnerabilities are so universal that an attack designed for one neural network will frequently succeed against a completely different one. The ultimate goal of defense research is certified robustness, a mathematical guarantee that a model will not change its prediction regardless of any perturbation within a specific limit. Achieving this requires fundamentally different training methodologies and verification algorithms that can mathematically prove the stability of a neural network's boundaries. However, scaling these verification techniques to the massive models currently driving the industry remains an unsolved problem. For now, certified robustness is largely confined to small, simple networks in academic laboratories, far removed from the complex systems deployed in the real world. The persistence of these vulnerabilities forces a reckoning with the true nature of machine intelligence. We have built systems that are incredibly powerful but entirely devoid of common sense. A human child knows that a panda covered in static is still a panda, because the child possesses a conceptual understanding of what the animal is. A deep learning model has no concepts, only correlations. The ease with which we can break these systems reveals that we have not yet achieved true artificial intelligence. We have merely mastered the art of high-dimensional curve fitting. This realization is driving a paradigm shift in how researchers approach the future of the field. Many experts argue that simply scaling up current architectures with more data and more parameters will never resolve these fundamental blind spots. Instead, the focus is shifting toward hybrid systems, often called neurosymbolic artificial intelligence. These architectures attempt to combine the pattern recognition capabilities of neural networks with the strict, rule-based logic of traditional programming. By forcing the system to cross-reference its statistical guesses with a hard-coded understanding of physical reality, researchers hope to create models that cannot be fooled by invisible noise. As the technical community searches for solutions, the regulatory landscape is beginning to react. Governments and international standards bodies are recognizing that deploying fragile systems into critical infrastructure is an unacceptable risk. New frameworks are being drafted that require mandatory red teaming and adversarial auditing before a model can be released. Companies will soon be legally required to prove not just that their software works in ideal conditions, but that it can withstand targeted, mathematically sophisticated attacks without failing catastrophically. This regulatory shift represents a fundamental change in how we value digital tools. For the past decade, the tech industry has prioritized speed and raw performance above all else. The existence of these exploits is forcing a harsh pivot toward security and resilience. We are moving into an era where a model's worth will be judged not by its peak accuracy on a standardized test, but by its ability to maintain its integrity when the world around it turns hostile. The metric of success is changing from how smart a system appears to how difficult it is to break. The battle between attackers and defenders will likely define the next decade of technological progress. It is a continuous evolutionary pressure that will ultimately forge more resilient architectures. Just as biological immune systems evolved in response to viral threats, artificial neural networks must evolve to recognize and neutralize mathematical pathogens. The vulnerabilities we see today are not the end of the story. They are the growing pains of a technology that is still in its infancy, struggling to reconcile its internal mathematics with the chaotic reality of the human world. Understanding these invisible threats is essential for anyone navigating our increasingly automated future. The illusion of machine infallibility has been shattered by the simple application of digital noise and physical stickers. As we continue to integrate these powerful tools into the fabric of society, we must do so with a clear-eyed recognition of their profound limitations. True progress will not come from blindly trusting the outputs of complex algorithms, but from rigorously questioning their perception, demanding robust defenses and ultimately building systems that possess the resilience to truly understand the world they are meant to serve.